Okay, so we're gonna do a recording that's focusing on recursion and makefiles. Makefiles is gonna be very brief. This is a very complicated makefile, so we're not gonna go too much depth, but I'm just gonna show you how to use it and not actually how to make one, right? I will show you how to modify one thing and that's it, and then we'll go into recursion. So this is not typically what you'll be given. It uses a bunch of other stuff just because it makes my life of generating these makefiles a lot easier. I can basically just copy and paste this wherever I want to change a few variables, which makes life easy, but it does make it harder to read. Like what the hell these symbols are. I don't remember half of them nowadays anyway. I did when I made this, but not now. The ones you care about is make. So what make does is it's going to go and generate all your files. You see it ran a bunch of GCC commands, and I have my file here, test, right? And I can go and generate tests. Like for example, if I want to run my test command, it's going to take a few seconds. It benchmarks a bunch of things. I don't even know what this does. We'll be changing the benchmark in a second. What does this do? It prints out a bunch of stuff. It runs find a bunch of times, and it runs a system find. Okay, awesome. Um, and we'll go into this in a second. You don't really have to care about this library. This library is just something I wrote. And you can see the source code here. It's on GitHub as well. It's a very pretty large library. There's two of them. This one here is a unit testing library, so it does a lot of my unit testing work. It's pretty got a bunch of features in it, and then this one's the benching library that does benchmarking, right? So this is used with the unit testing library together to kind of form a duo. Um, And so this is what gives me all these nice benchmarking results, which also have logs and so on that you can look through. Though I haven't actually decided to trim out these are color codes. That's why they look like this. I probably should at one point try to trim those out. Anyway, and if I make clean, it'll delete the logs as well, which is quite nice. So they're the two ones you have to care about is make and make clean. Sometimes there'll also be a make all. So there's no make all in this case, but the reason why it's make all is if, for example, a lab has multiple sub make files, and you want to be able the ability to make all those files, and also make them individually. So if I wanted to make, let's say, I don't even know what an example lab exercise name would be, but I think like I was one could like remove vowels, so that's probably the name for it, right? And so that would be the makefile name, right? Obviously, in this case, yeah, I don't have that makefile, so it won't show. But you'll be able to just open up the makefile, and what you're looking for is things that look like this or like this, right? So it's probably going to look like this more like. And so if every time you see one of these are things that you can execute. So you can have a look for your makefiles. The only other thing you have to care about is the fact that you can change this GCC to DCC, and you'd be running, you guessed it, DCC, as you can see here. Right? Which is obviously going to complain because I'm running locally without DCC, right? But I could change it to be Clang and it probably will work, right? Um, yeah, and it works fine. I really have no preference between the two, so I'm just going to go with GCC. And the nice thing about make is they will only recompile files it's needed, as I said before, so it's not going to recompile stuff that you don't need. So for example, if I go and update tests and add an extra line, it will just generate the tests and the output, and it won't generate the Fibonacci function, right? Which is quite nice. As you see, it won't generate this fib.c. Yeah, so you don't really have to care about that, but it may be somewhat useful to you. Anyway, so what we're going to do is we're going to begin with building Fibonacci 3 times, and one of them will be similar to the lab one, or I mean, probably identical. Um, and that's somewhat intentional. I don't mind giving away lab solutions if it's towards the end of a week. I will leave that to a very, very last. I do recommend, I will give you a warning when I get to it, to work on the lab and try to complete the lab before you look at the question, because we'll cover enough information that you may have an idea of what you want to do with it. Um, and if you are going to watch it and you haven't completed the lab yet, try to watch it slowly and try to like stop it, then maybe do a bit of lab and continue it and see how you go, right? Rather than just like watching and going, yeah, I understand all this, this is fine, and then you have to do an exam and you don't know how to do it, right? So make sure you can actually do it. So the first thing we're going to do is just include our recursion file here. Now, obviously, you notice that these are in different directories. The reason this works, I mean, it's going to complain here, but the reason this works is, and then it's not going to complain anymore, is because up here I've got this include directory. That basically means we're going to include everything inside my include directory, right? So it's pretending like everything inside my include directory can be accessible from here, which is a nice thing, right? And sometimes we often do that to save us having to do weird things, especially if this is all inside a source file directory, then it kind of gets a bit awkward to try to like find the correct path. And also means if you move files around, it becomes messy. Okay, so what are we doing? let's just start off with building our 3 Fibonacci functions, then we'll give them quick benchmarks and kind of show you what I mean. So we're going to do a bit of what we call big O analysis, which is like basically looking at how efficient a function is as it grows. Um, but we're not going to spend too much detail on that because that is not that important. So first off, we'll begin with fib recursive, and then we'll do fib upwards, then we'll finally finish with fib memo. And we'll also probably do a bit of linked lists and structs as we go. I'm not going to make this more than 20 minutes. I say that, we'll see how it goes, but hopefully. So fib recursive is really, really probably the simplest version here. And I'm just going to probably pop this up next to it so I can look at the comments and kind of show what I mean. So fib recursive is just basically this, right? That's what I said. And so what we can do is you can basically just match these conditions here, which is what this is, to the value. So we can just say, hey, if n is less than or equal to 1, then return 1, else return fib of n minus 1 plus fib of n minus 2. Now, there's a note here that some people define fib slightly differently. I define it as 1, 1, 2, 3, 5, 8, 13, and so on. Some people add a 0 at the front. Those people are probably wrong, in my opinion, and the course will typically present it in this way if we're giving you a Fibonacci function. I don't actually know how this week's one is presented, but I presume it's in a similar way. If it isn't, then you could always add the case. If n equals 0, do this, and if n is less than or equal to 2, right? But I prefer the 0 indexed Fibonacci. I just think it's simpler, and it also just makes more sense when you actually do anything with Fibonacci. Fibonacci doesn't really make sense when you have 0, because the whole point of Fibonacci is that the previous two numbers add to get to the next number. And like, it makes sense that you'd have 2 1s to begin with, but to have a 0 and a 1 to begin with, just, I guess it technically makes sense. It just doesn't. It's the only number that could precede it that would make sense, but it's still a bit weird. Anyway, we're just going to generate that, and that's fine. So we're done. Right? This is basically all this function needs to be. Now, if we want to go upwards, this isn't going to be recursive. Now, I'm going to talk about what this means in a second, but for now, we're not going to talk about it, right? So for now, I'm just going to say pretend that this is just a mathematical definition, and then we're going to look at the performance of the two, and then we're going to analyze why that performance is slow, and in doing that, see what recursion actually is, right? So we're not going to look at recursion right now in terms of in-depth, right? We will in a few minutes, but right now, I just kind of want to conceptualize that all it basically is doing is mapping to this function, which is basically saying to find out what the Fibonacci of 1, 0, 1, 2, 3, 4, 5, 6. Find out what Fib 6 is. You find out what Fib 5 is and what Fib 4 is, and then you add them together to get Fib 13. And to find out what Fib 4 is, you've got to find out what Fib 3 and Fib 2 is, and so on, right? And that's what recursion basically is. It's not so much the function's calling itself. I mean, yes, it is. But it's more about the concept that the function is eventually going to terminate at some kind of eventual point. And the idea is that you're making the object smaller and smaller and smaller, and the space at which it's performing at is smaller and smaller and smaller, right? If it's getting larger and larger and larger, it's probably not going to terminate. You probably got problems, right? I guess you could still classify as recursion, but it's not typically the recursive problems that we solve. And we'll go for a linked list example, which tie everything up and make everything make sense. So going upwards is not going to be recursive. And the rough idea of it is that basically we're just going to say, we're going to calculate what 0 is, we're going to calculate what 1 is, and then we're going to add those together to get the next one. And then we're going to add the previous one with that one to get this one, and then we're going to keep going, right? So we're going to start at the very beginning and work all the way up rather than working the way down, right? So we're just going to say int a equals 1, int b equals 1, and before that, we're actually just going to check. This just makes the code a little bit simpler if we just still check the less than or equal to 1 condition. Then all we're basically going to do is we're going to say int I, which is kind of like our counter that counts up, and we're going to set this to this first position here. Or rather, I guess we're going to set it to this position, if that makes sense. So we're going to set it to 1, and say while I is less than n, right? We're going to set, I guess, a temp to equal a plus b, right? And then what's going to happen is a is going to be the first one. I guess we could call one like previous. We could call this current, if that made sense. So if we want to do that, that's fine. So in this case, we'd say that, you know, the previous one. Well, it's not really true. The temp one is going to equal the previous plus the current, right? and the previous one's going to equal the current, then the current one's going to equal temp, right? There's other ways you could write this, but that's kind of effectively what we're doing, right? So if we look at it in terms of a slow operation, we start off with, previous equals 1, current equals 1, and then we're going to go temp equals 2, previous equals 1, current equals 2, and then we're going to go temp equals 3, previous equals 2, current equals 3. If that makes sense. You can kind of see how it's like progressing its way up. Okay. And then all we're going to do is basically once it reaches n, return current, right? So for example, when this phase begins, the value of I will be 1, which is this position right here. And then when it tries to calculate, let's say, fib of 2, what's going to happen is it's going to get to the point where it goes, okay, at this current position, it's less. I guess I should also increment I. It's going to go, okay, currently I'm less than 2. So what I'm going to do is I'm going to proceed to the next element. It's going to add previous and current together. So it's going to grab 1 plus 1 is 2. It's going to set previous to 1. It's going to set current to 2. And then it's going to increment I. I is going to now be 2 is less than 2, which is obviously false. So it's going to stop. Now, I'm sure some of you probably noticed that the fact that we don't really need this less than equal here because it could be less than, because if it's equal to 1, then it's going to stop immediately and return 1, right? And arguably, we really don't need this at all, because if n's 0, then it's also going to stop and just return 1, right? So you don't really need that if statement here. This will work regardless. I'm just going to include it just because I think it makes the code look cleaner. But I will put a note saying not needed, since if n is less than equal to 1, then I will be not I is greater than or equal to n, right? Because either I is equal to, I mean, this is obviously going to make sense, right? Because basically I is equal to 1, so we're basically saying 1 is less than or equal, or rather 1 is greater than or equal to 1. Or I guess it's more like, it's weird, but you can kind of get what I'm saying. Hopefully. So that's it. And those are two functions. We could test them out, but I think the easiest way to do it is just to build some tests. So to build some tests, luckily it's pretty easy with this library. All we got to do is we don't care about system tests or most of this stuff. All we really care is about generating some benchmarks. So we're just going to say this is going to be fib recursive. We're going to run it 100. We're going to run it like 1,000 times, right? So what this basically means is that we're going to run each test 1,000 times and average the results effectively and show you the standard deviation. So it's a little bit complicated, but that's okay. And then we're going to loop for every value in Fibonacci from, I guess, I'm going to loop from 100 to 200. But I feel like that's already going to be too large. What's Fibonacci of 100? Um, is it really large? Yeah, that's too large. Yeah. Okay, we're gonna go from 10 to 30. That may also be too large. It's just because recursive is really, really slow. So having it generate may just kill my computer. I'm just gonna run it 10 times also, just because I do not wish to kill my computer. Okay. Now we're gonna run this function here. Now the important thing here is that we actually do want this to actually execute. So we are actually gonna assign it to something called a volatile int. Now this is just an optimization technique when we're benchmarking. What this basically means is because this is volatile, it'll have to do the right. It can't just like remove this code, right? Because what it will probably notice that Fibonacci isn't doing anything. So hey, I can just remove it. Like it's not going to change the program, which is not good, right? So we obviously want it to remain. And so we're going to run this. We're also probably going to, I don't know what optimization level we're running on, but we are going to drop it if it's too high. Currently nothing, so it should be fine. But if it was, we would. Okay, upwards, and then we're just going to obviously run fib upwards, right? So it's the exact same code between the two. And furthermore, we're actually going to run upwards first, just because it's going to be faster. And we're going to open up a terminal, and we're going to run it. So this is our code here. We're just going to run a make. It's going to generate our tests. And we can rest run our test here, right? And we can see that upwards was 0, recursive was 0.014, right? Okay, so let's increase the numbers a bit more. So we can go from, let's say, 100 to 200, right? Maybe I was wrong. Maybe this will be fine, right? Oh, it's still fast, right? Which seems wrong. It's actually executing the code. That's gonna be fun. It's just because when I see stuff like this, I'm like, because like if I look at the Fibonacci for 100, for example, uh, it is that too big to fit into int? Yes, it is. So it's probably not executing. It should be because of the int. Yeah, let's just do this. That will force it to do something. And same thing here. It could just be where it's fast for some reason. There we go. So the volatile did not work. It still tried to optimize it away, which is fun. Now this is just going to kill my computer because it's too much. But we're going to basically reduce it down to what it was and let it execute. And make it first. Awesome. Okay, that probably could be a bit larger. It's the problem with this stuff is because it's n squared, as we'll see. It's a bit hard to like guess the range because it just increases so fast. I'm just gonna do a proper make clean before I do anything. Okay, that's looking a bit better. It's generating files. Force it to. I can see how well it's doing by probably looking at these files. What's the files afterwards? Guess I won't be able to. And we'll just let this run. If this takes more than another 10 seconds, I'll probably just reduce the range. Okay, I'm going to reduce the range. Okay, so we're going to reduce the range. We're going to begin by just trying to reduce the range on this. Yeah. So the problem is definitely recursive. As you can tell, this is generating this perfectly fine. So this is going to be a bit fun, but I'm just going to try to like find a range that makes some sense of recursive without being crazy. Okay, this looks a bit better. That's significantly better. Okay, so we're just going to increase the range a little bit. We're going to reduce the number of times it runs, which is going to hurt the accuracy, but it will also save us having to wait for 40 minutes. And then we're going to remake this. And then this is going to be my final thing. I'm not going to touch it after this. Obviously, I'm printing out the values, which isn't great, but it's the only way I can basically force it to create a side effects I can think of. There's other ways I know you can do it, but like, I don't remember them right at this moment. It's a bit late. It's almost 1 p.m., 1 a.m. So the big thing we'll notice here is that clearly this function is insanely fast and this function isn't, right? And the main reason why is just due to the rate at which it scales. And so this is coming back to what I was talking about recursion before. And so what we're going to do now is we're going to go into basically a mode where what we're going to do is we're going to like expand the tree and try to understand what the tree is generating. And so let's just do that within our fib file here and try to like understand this as a graph or more like a tree, but I guess in some cases it could be like a graph. So let's try Fibonacci of 5. May seem pretty small. This would take us probably 2 or 3 minutes. So Fibonacci of 4, 5, we can already know it's going to be Fibonacci of 4 plus Fibonacci of 3. Now, I'm already scared that I'm not going to have enough space, which should be a pretty decent concern, right? So I'm just going to move this across a bit, and then also just make these go out a bit so that we have a bit more space. Okay, so then we have Fibonacci of 3. And again, this is going to go out a bit. Though honestly, there's probably a better way of doing this. To the face-to-face tunes if you want nicer diagrams. I tried to do diagrams in previous years, like with a tablet. It just doesn't work the same. There's just severe problems with it. It just like it's not so much the tablet. It's just like awkward. And it just doesn't work the same as if a whiteboard. So then we have this thing here where we're going to find the Fibonacci of 3, right, and Fibonacci of 2. So Fibonacci of 2 can be pretty small, right? And already, hopefully you can see that these things are going to collide. And this is also going to be the Fibonacci of 2. Now, for the sake of my sanity, Fibonacci of 1, I'm not going to evaluate Fibonacci of 1 further. I'm just going to stop there. And Fibonacci of 2, I'm just going to fully evaluate like this, right? Obviously, Fibonacci of 1, I guess you can't really evaluate anyway, right? Because that would require Fibonacci of -1. So it doesn't really matter. It's not even my sanity. So this is effectively what's going to happen here, and we're going to have the same thing here, right? Fibonacci 0, right? And Fibonacci of 1. So hopefully you can see how fast it's expanding. And the other thing that you should notice is there's a lot of repetition, and this is really important. And this kind of same thing is going to happen with 3 here, right? And so we could just copy and paste this like side of the tree, right? In reality, I guess I would do that just for the sake of it, but it's probably not needed, right? So this would be Fibonacci of 1. Again, I'm not going to don't need to do that, but Fibonacci of 2 I should probably do, right? So Fibonacci of 2, this is Fibonacci of 1. You can see how my lines are starting to be a bit more marked up, right? But hopefully it still kind of reads okay. I'll make a better diagram when I like upload the code. And then we have Fibonacci 1 and Fibonacci 0. Okay. So these are basically our entire tree. So for Fibonacci of 5, we've grown quite a bit. And the interesting thing is how this grows. So for every function call, we create 2 more function calls, right? And in kind of the modern era of kind of COVID, there's an interesting, like, I don't know if I would say particularly interesting, but there isn't a kind of curious, I guess you could say, side effects in terms of its relation to saying in the real world, right? And so the basic idea here is kind of related to what we typically call, though it's too late for me to remember. It's like R index or something. It's like the index for like a virus in terms of how fast it spreads, right? And so if you have a R index of 2, whatever the actual terminology is, it basically means that like it spreads that exponentially fast, right? As a rough understanding, I'm no virologist. So in this case here, right, this is spreading such that for every member, there's 2 outgoings, right? And this keeps going until you reach like these endpoints here, right? And obviously it has to reach endpoints, else it will never terminate. Um, and so what that means is that you can kind of visualize how fast this will grow and how fast this will expand because you've kind of had some real life experience of how fast this stuff does grow and expand, right? Um, and that's really bad for computers because you're basically making them do more work. And a lot of these common things could be remembered. And that's what a memorization function does. Now, upwards does not have this issue. And the main reason why is that you can see here this while loop can only run a maximum of n times. Right? There's no way for it to run more than n times. Whereas this isn't running 5 times, is it? Right? And so the growth rate of the functions are very different. And there's a few ways you can analyze growth rates. I'm not really going to go into it. I was originally, but now I'm thinking about it. It's not really relevant. You can look at it if you care about it. And the only thing I will show that does kind of show this is here, T3, 1521. Okay, here we go. So we're just open at 1521. And then what we're going to do is we're just going to chuck open the the Bigo tool. And we're just going to look at, I believe I've got a Fibonacci function here once it says grow. I do not. That's fun. I don't have recursion in here. That's okay. But the big thing here is if we just take any given function, right, we can see that as the rate grows, because there's no function support. This is a language I just quickly wrote up like 2 years ago. And I was always meaning to add function support to it, but I never did. And so if we look at for example, this function here, we can see that this function is most likely, I believe it gives a guess, is on log n, right? I can look at, for example, two stacks, and this is o log n. A maximum is on. I mean, it says could be something else, but probably not. But this one's going to be on squared. And we can see how fast this rate actually grows, right? And you may go, well, this doesn't look like on squared, right? Because on squared grows this fast, and this is growing so much faster, right? But as soon as we do like on to the power of 2.5, you can see how it's definitely not this, right? And this is effectively what we call constant factors and stuff like that. And so what we're doing is we're basically looking at kind of like the rate of growth more than just like the specific way the function grows performance-wise, because that could change a lot per machine. So we're saying, well, if I double the input speed, if I double the input size, well, what do I expect with the input output? Like how fast is the program going to run? And in this case, I'm measuring primitive operations. You can see there's quite a few primitive operations, rather than actually measuring raw performance. And the main reason there is because the performance here will differ a lot per computer. And I kind of want to give you a rough idea of the operations that are being performed in this case, rather than the actual performance. It's the same kind of idea of a metric. It's just a bit more better to do with a JavaScript engine that won't necessarily have the same performance as C. Um, Anyway, so you can see that the grave growth here is quite high. And this is kind of like the main difference, whereas our on function is effectively this. You can see there's a massive difference. And so now this kind of makes sense why there would be such a massive difference here with this, right, for our benchmarks. We can have a look at the benchmarks here, right? And the important thing here is to recognizing, is this on squared or is this like some kind of exponential, right? And the answer is, well, what do you think, right? Have a think about it. Right? Just like in your head, go, well, okay, if it's doubling every single time, right, the number of possible outputs, is that going to be on squared? Is it going to be on to the power n? Like obviously it's going to be one of the two most likely, right? I'll give you a few more seconds to just kind of think about it. So I've kind of showed you what on squared looks like. I'll show you. Do I have on to the power n? I do not. It's very fast. You can look at like an exponential to the power n. Yeah, so you can see to the power n is this orange one here, on squared is this one here. Now, the actual fact is that Fibonacci numbers do not grow as either. So it exhibits exponential growth, but it's technically not exponential. But for a large enough number, it's basically an exponential, right? And I believe it uses the golden rule. You'd have to Google to really figure out, but effectively, it's an exponential that's roughly, very, very, very roughly O to the power, 2 to the power n, very roughly, right? Um, but it does grow at a very different rate. I believe it uses the golden rule as a specific rate of growth, and the reason why is I think mainly due to the fact that it terminates in kind of like a weird way. Um, and like the numbers get larger in a weird way too. Like it's not so much. I guess the numbers themselves also grow in a weird way too. Um, but the actual number or the count of the sequence will be 2 to the power n, right? The specific number of items in the sequence. So the values aren't going to be exactly exponential, right? Even though they do grow very fast. But the actual number of each items is going to be exponential, or is going to be 2 to the power n, because you can clearly see it doubles every single time, right? There's 2, there's 4. Technically, there's 6 here. So I guess in this case it isn't, right? But like this 1 is a very small case. If it was large enough, it wouldn't be that. And that's kind of like the point, right? Is if you make it large enough, then this would also have children, right? And so it will effectively double. Um, yeah. Anyway, hopefully that made sense. Let's keep going. And then we'll stop basically here. There's not too much more I want to go about. So the rough idea of recursion is this concept of, I like to think of it as like boxes, right? And so you're taking a large box that represents your entire program space, your entire problem space, and then you're making that box smaller and smaller over time. And so to begin with, the entire program space for this Fibonacci represents this entire thing here. And then we're stating that, well, the value of this can be calculated by grabbing the program space, the algorithm space of this box that just consists of 4, and the box of 3, and then adding them together. So basically, you're splitting the problem in half. And you're repeating that splitting until you basically end up with what we call an atom problem, which is a very, very small problem, right? And so we'd call this an atom, right? This is just a definition. It exists elsewhere. I was taught it too. I don't necessarily know if it exists online in a specific form, but this is, I think, an easy way to understand it. And so this atom is like the smallest possible unit. It's the smallest possible function call. It doesn't require any recursion. It's just instantly evaluable. And then we build up these atoms to form our entire Fibonacci, right? And this always occurs. Atoms always are the basis of everything, right? Because you eventually have to terminate. And so if I give another example, oh, okay, yeah, I've got 2 recursion files. And this other example is, I won't actually benchmark this, but if this other example is if I create a linked list. And the important thing about a linked list is the linked list itself is recursive, right? And we'll see why in a second. So basically, this linked list has 2 things that's important to it. The first thing is the linked list contains a pointer to the next element, right? So if we visualize it again as a series of boxes, we basically end up with something like this, right? This is our first box, which could be like 1 or something, right? And this contains a pointer to the next box, right? Which for my sanity, I'm probably just going to do 1 by 1s. And so the next box is just going to be, let's say, 2, and then maybe it contains a point to 20, and then another box to 140, right? And the key thing here is that this is just a pointer to the next box, right? But this box could be located anywhere, and this is the same thing as I went through the tooths and so on, right? Pointers have, an address, obviously, but they also have a value, and their value is where they point to. And so by chaining these along, we can have like a long series chains of connections, right? And then eventually this chain will terminate with null. And whenever we have a recursive data structure, it makes doing recursion on it very, very, very easy. And so to do recursion on this, all we have to do, which is lucky, is I don't know, let's just have a function that counts it, right? So we're just going to take in every element, right? What we have to do is think about the base case and the recursive case. So in this case, what's our smallest case possible? If our entire box is this entire list, and we want to sum up this list, think about one element that you instantly know the sum of the list. So if I give you a single list in the world, any list whatsoever, can you immediately figure out the length of that without having to visit any of the pointers? Like maybe, I don't know, say in your head, say it out loud, something like that, right? Think about it and go, is there any list? Some of you may say a single element list. That's okay, but you go check the pointer, don't you? That is technically a valid answer, but you are checking the pointer. So it's a bit different. The answer here would be an empty list or null. If I give you null as a linked list, that basically represents an empty list, right? That's just the convention. So if I give you an empty list, you clearly know what the count is. That count of an empty list is going to be, I'm going to say 0. So I can say this, return 0. I can also write like this. I can write like however I want. I'm just going to include this and this just in case I want to use anything of it. For example, null. So here I'm just going to check if it's null, right? This is the same thing as saying this right? And I talk about it in the Friday shoot video, in a little bit of detail. Okay, so we've solved the smallest possible case. Now, all we want to do is we can do two things. We can either start the biggest possible case and try to go smaller, or we can start the smallest possible case and try to go bigger. And so from the smallest possible case, what's the next biggest box we can take? Well, it's obviously just going to be this. Like, this is the only program space that will include null, right? That isn't just going to be the entire thing. And so what we're basically saying is we have a one element list, right? Then we can find the sum of that by grabbing the value of the object and then adding it to the recursive of the next part. So basically then this just becomes return current data plus count of current next. Does that make sense? So what we're saying here is we're saying grab the value 140 and add the count of the next element, which we know is null. Right? Obviously, we could check and go, okay, if this is null, if you know, um, current next is equal to null, return just current data, right? But like the point of this is if you're building up like this, you kind of want to like choose something that's generic. But you could do something like that, then you would have to go to the next one, it'd be current next is null and so on, and like you're basically just hard coding at that point, right? Which won't work because it won't expand fast enough. But you can kind of see the way the pattern works, right? The key thing here is what variables are you looking at, and see this variable that we're looking at. If we keep expanding this, right, and we keep like hard coding it, we notice something very interesting, right? So for example, if we expand it to 20, we notice that what we're doing is we're going to grab 140, or rather in this case 20, I guess, add it to the next one, which is going to be 140, and then obviously we don't have to add null, and then we can keep going, and hopefully you should start to see what's happening. Right? What is the part that we're recursing on? What is the part that we're repeating? It's next. And so that's what this is doing, right? And so that is a way that you could do it. I guess I'll keep these as comments, right? Is that you could try to like repeat it outwards and try to understand that way. The way I like to think of it is I take the biggest box possible after I figured out the base condition, and all I do is I say, how can I get the next smallest box? And the only way I can get the next smallest box is by taking this, and the only way that I can kind of reconcile these two differences is by adding the counts between them. Yeah. And if you wanted to count how many elements there were, let's say a length function, what would you do? How would you change this to make it a length function? Right? You only have to make one change. I just want to count how many elements there are. So obviously, the length of an empty list is nothing, 0, right? What would the length of a single element list be? Or if you said 1, what would this element of a double length be? 1 plus 1, 1 plus 1 plus 1. Okay, wonderful. I am obviously not talking to anyone, right? Which does make it kind of weird for me. I actually have to like imagine people talking. I think this is a slightly easier way of giving these talks, so I don't go insane. Um, Hopefully it's fine at your end. And so in this case, we're just obviously going to repeat that pattern, right? 1 plus the length of the next element. And it's going to go 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. And again, this is kind of what we're talking about atoms, right? The atom here, the smallest element, are ones and are zeros, effectively. And we're summing them up to form our massive list. Okay. Now this seems pretty awesome, right? These are pretty short functions, but like if I wanted to write it the long way, how would I write that? Int length while. Well, you would just have to write a while loop, right? You would have some kind of sum, right? And you go sum is plus or equal. I guess this is length, right? So length is plus or equal to us. And then you go current equals current next, right? So you're moving the current element to the next element, and then you're gonna see if it's null. If it's not now, increment the count, and then keep moving, right? So it's recursive. You don't really have to care about recursive structures in this course at all. I just think it's the best example for recursion, right? Because recursive structures obviously need to use recursion. So it's just a good example. I don't think it's a better example, which is why I'm using them. So again, to swap it to sum, we just swap it to sum. And in this case, it is shorter. It doesn't always necessarily have to be shorter. But the key thing about recursion is that you're trying to simplify a problem by making it smaller, right? Choosing the biggest program space you can and just shrinking it over time. Okay. Now we have a very fascinating thing next. I say this and I'm hyping it up. It's not that fascinating. And it's calculating the fib memo. Now, I'm sure a lot of you wanted me to do this. And probably skip forward. If you skip forward to this point, it's fine. I would probably too. I would just probably recommend that you go back and you just do some of the last probably 10-15 minutes, because that's probably the more important part in terms of understanding structs, right? And I guess I don't really want to cover structs in that much detail because I feel like structs as a concept aren't that hard, except for when you get into recursive structs, which I just kind of covered. Um, but really, all you're doing is just grouping data together. So rather than having to allocate this separately, you're just saying I can allocate it together. That's it. Like there's really nothing else to do with it. Um, that's all you're doing is you're just allocating the data as one segment rather than like keeping them separate, right? So it's just a grouping. It means nothing to the compiler past the grouping. Um, we'll come into structs a bit more when we calculate the size of the structs, but that's later. Um, okay, so if we want to memorize this function, the first thing we need is we need something to store the results. So all memorization is basically doing, there's a few interesting ways, but the rough idea of it is that you're just storing all the results of the previous executions of the function inside the function, right? Well, not necessarily inside the function, but somewhere. So we could create a variable here, and we'll see there's a reason we won't do this later, but for now this is fine. And for your lab, it's fine. And we're going to say you can have up to 250 elements, right? And we're going to begin by inserting two ones, right? And what this is basically going to do is going to insert two ones, and then the rest will all be zeros, right? Because when we do stuff like this, it has to initialize every single value, and we've only given it two values, so the rest have to be zeros. Um, so the result of this will be 1, 1, followed by a series of zeros. Now, this is really important for us, and this is one of the reasons why also I didn't define Fibonacci to have 0 in it, because it allows us to determine whether or not a result has been retrieved or not, or has been calculated or not, based on whether or not it's 0. If it's 0, we know we know it's not been calculated. So all we have to do is we have to go, hey, if fib array of n, right, is equal to 0, or this, right, then return fib array. Sorry, does not equal 0. Then return fib array of n. You could also write like this. I think this looks clean, right? I'm going to say, hey, initialized to 1, 1 followed by zeros. Zeros mean no calculated value for that n. It's so late. It's not really that late, but it is a Friday. So in this case, this February here is my brain is dying. What am I saying? Okay, if it has a value, the the fib array of n will be non-zero. Sure. Okay, so if it doesn't have value, it will not be non-zero, i.e. it will be 0, and we can calculate the value. So we're basically just going to calculate it using recursion. The reason why will become slightly more apparent in a second. We don't really care about that because like we already have like less than or equal to 1. Like it's right here. And what we're going to do is we're going to say fib memo n minus 1 and fib memo n minus 2. Now, we're not going to return this immediately, though. We're actually going to write into the array. And we're going to say int res equals this. And then we're going to say, oh, I guess how about we just do it this way? We're going to say if this equals 0, there's a reason why we're doing it this way. Then what we're going to do is we're going to write into the array, and then we're always going to return fib array of n. It just will make the code look a bit cleaner. And what we'll do here is we'll set n to this, right? So if it's equal to 0, it will calculate the element, write it into the position, and then return it. If it does not equal 0, it will just return it. So what this means, the reason why this will only calculate things once is because when it gets to 4, it will calculate 4. And when it gets to 3, it will calculate 3. But when it gets to this 3 here, it's already calculated 3, so it won't do it again. And so we can only calculate each value once, and there's only going to be n values, therefore it will be O(n). Furthermore, if I call the function again, it will be even faster than this. So it just gets faster. Now, if you're on Friday too, because we talked about this a bit more, then hopefully some of you are starting to see something that we can improve this code by. If you're not on Friday shoot, but you watch the video, you're maybe in the same boat. If you're not in any of those groups, I don't expect you to see this, but maybe you do. What can you see? Have a think about the code and have a think about how relevant is this variable to the rest of my code and whether or not I can hide it. And the answer is yes, I can. So we're going to hide it in here using a static variable. Because remember, static variables exist throughout the lifetime of the program. And this is a major benefit of static variables. This and the other one I gave with a singleton. They're basically the same thing. Pretty cool, right? Okay. I'm pretty much done. I'm tired. I'm going to stop the recording here. Hopefully this gave you a decent introduction to recursion. Recursion's a pretty hard topic. It's not easy. There's a bunch of stuff out there. I think the only way you can do recursion problems, or the only way you can learn recursion is by doing. So I recommend just Googling recursion problems, trying to solve a few. Maybe try to like look through go back through your linked list notes if you have them and try to like solve some of the linked list problems using recursion. Things such as reverse linked list is pretty hard using recursion, so it's a great thing to do. Stuff like that, right? Linked lists are not relevant whatsoever for this course, so if you don't remember them, just forget them. It's okay. It's probably not worth the effort to look them up. We won't cover them whatsoever in this course. Well, yes, we won't cover them. The only case we would do if we did malloc. Malloc requires linked lists, because it does include a free list. But we don't do that this year or this sem, so you'll be fine. So you can kind of just forget it. Anyway, this code will be pushed. I'll add a link in the email. Hopefully you've seen that and you can access the code that way. You should just be able to run it. Like it should just work regardless of a system you're in. These are single header files that will work wherever. If you want, you can try to look for this craziness. If you really care about where this code comes from, you can go to my GitHub, right? And on my GitHub, it should have the links to at least one of them right off the bat. Well, my GitHub won't look like that. My GitHub will look like this. If you just search GitHub here, Braden Whitting, I will be the first result. Here, you just click my name, and you'll be able to see my results. Right. And so the one things here is that the Obsidian library, if you want, you can follow it. Have a look here. You can star it if you really want. I just use it personally. I haven't really released it for other people. Main reason why is because we don't support Windows for benchmarking child processes. It will support Windows for benchmarking other things, though it's not really that well tested, so it may not work, but it will work on CSE, right? And so you can read through the guides if you really care about using it for your stuff. It can produce some really awesome results, telling you like errors of assertion failures and stuff like that. I use it for a bunch of things. For example, we may find in the future week, I may go through this if people want to know more about linked lists or other data structures. I've built a linked list visualization library that works with arrays and stuff like that. And you can see this is a super sped up version of it. Normally it's much slower and you press space to go one by one, but it's a cool little visualization tool and it uses this to do its benchmarking. I don't really know why I'm showing this, but I guess you can see here. All right, so it creates all its testing here. You can see the test groups and so on, and it's quite nice. Awesome. This is actually a really cool project. This is like a real proof of concept of like actually developing a C project that exists in the wild and stable. That's kind of cool, but I don't care too much about it right now. Anyway, as you can tell, I haven't touched it in 2 years. Probably need some updating. Anyway, thank you so much for watching this. I guess, and see you guys next week.